So today, we are going to continue from where we stopped last time. So which is looking into the categorization of ensemble techniques. So you can categorize them into what we call the heterogeneous or the homogeneous. However, before we go ahead, so let us refresh. Let's refresh our memory, what we did last time. So remember last time we discussed about how do we build and assemble the base classifiers. Because specifically there are three stages in building and assemble. The first stage is to try and construct as many base classifiers as possible, or as you want. For instance, I want to build an ensemble that will make use of like 5 different base classifiers. So we need to decide how we're going to build those, develop those base classifiers. Further also, we remind ourselves about the summary concept of ensemble, how it is a very unique way for you to escape being caught up in producing very poor model. That in real life, sometimes when you use your data on individual models, like we have here, this is a model train called model 1. It's able to achieve 57% accuracy. Model 2, 57.14, like that. These two got the highest accuracy, 71.43. But with the power of ensemble, we are able to achieve 100%. So this is why ensemble is very, very important. We continue to remind us about this. So it means sometimes when you are struggling with coming up with an individual model that can achieve your aim, but it seems it's getting impossible, you might have to proceed to try to see, okay, what can I get if I go for ensemble? And we describe some of the challenges, of course, the computational complexity, the time you're going to spend. But however, if you really think it's worth it, for example, in this case now, it is clear that yet it's really worth it. If I can go from maximum of 71% on individual to a combination that we achieve 100%, that is 30% improvement over the best one. So to me, whatever is going to take, it's really worth it. However, if I'm getting 99% accuracy on an individual single model, does it worth it to say, okay, I want to get 100%, I'm going to spend another maybe week or month building another ensemble? So it depends on the kind of problem you are solving and the requirement you agree, that is agreed upon between the developer and the client. So in summary, this particular example always tells us that in most cases, you are likely going to get better results with an ensemble. This is a classical demonstration of such. And I told us that it's in line with the natural system we use. When you have a group of people, that's why they used to say that 2 more good heads are better than individual heads. If you have experts in a particular field collaborating together, they are likely going to produce better results than an individual in that same area of expertise. These are established facts that we all know. So in the same way, machine learning tries to take advantage of this and see how can we improve performance accuracy of our models by through combination in a smart way. This is what we call ensemble. So on last week we described how we can construct the base classifier, because the first step is to build the base classifiers. You have to develop different models that you are going to combine later. See? Basically, there are like 3 steps you take when you're building ensemble. The first step is you have to specify a number of base classifier. We call them base classifiers. Or sometimes we call them weak learners also. That is, it is considered that individuals are weaker compared to when you combine them as a team. So how do you build the base classifier or the weak classifiers? Because these are those that you are going to combine later. So when we described last week that there are four generic methods of building them: manipulating the training sets, manipulating input features, manipulating class labels, or manipulating the learning algorithms. In this case, we said this is where you use resampling to produce different versions of the same data set, either using sampling with replacement, sampling without replacement. We already discussed it in our previous videos, and we recommend that we watch it, especially for those that are just joining us. The manipulating input features, sometimes you need to play with the number of features. This is especially if the number of features you have been given are so many. So you have like 500 features. Instead of reducing them arbitrarily, why don't you break them down into a group of features? The first 10 to build one, another 10 to build another one, another 10 to build another model. You keep building different versions of these particular models that you are going to combine later on. Sometimes you might need to also manipulate the class labels. We also discussed this, especially when you have so many classes that you want to predict. Usually the base is the unique one is to have what we call the binary classification problem. Binary classification problem, whereby you just want to classify maybe someone is diabetes or not, yes or no. We call it binary classification problem, which means you only have two options, yes or no. But in real life, sometimes we have problems that are more than that. You need several predictive classes. For instance, you want to predict if a student is going to get A+, A, B+, B, and continuously up to F. So this is called multi-class problem. So when you have multi-class problem, sometimes the more the number of classes from experiences, then the more difficult to get excellent results, actually. So in that case, if you suffer from inability to produce better model or individual model, then you might need to try manipulating the class label while generating your ensemble. In which case I can decide to change. I can break them into binary classification problem. I want to get those who got A+. Did you get A+ or not? Or not? It means I'm going to consider A+ data as one class and every other person as another class. This is called relabeling the classes. So when I want to build another one that will recognize A, the person who got A, the data set will be one class, and then the other one that did not get A will be the second class. Up to the time I get F. Those who got F will be class 1. Those who doesn't get F will be class 2. So it means I'm going to have several versions of the same problem while relabeling this data set to come up with binary, several places. And then I use them to build ensemble, and then we can do the voting later or whatever combination. And then the final method we described was manipulating the learning algorithms. That sometimes you just need to change the learning algorithm you are using, like changing the topology of a neural network. You started by using 2-layer neural network, you move to 3-layer, you move to 4-layer, you up to as many layers as possible, or you are just playing with the number of neurons in a particular single layer. 2 neurons, 3 neurons, 4 neurons, 5 neurons, etc. So this is what you can do. We discussed this extensively. So that is how to generate base learners. Now, reference should be made to the last week video for more details, especially for those just joining us. So, and then finally, we also mentioned that while building it, we could have what we call the MultiClassifier System architecture, where you have the serial one, and then we have the serial one, and then we have the parallel. Serial means while building, we build one before we move to the next. And we say this is applicable. This is applicable for the case of boosting. So we are going to discuss them in details later. And we have parallel. This is one that is faster because everybody can build whatever you want to develop in parallel. This is by participant 1, participant 2, up to N. So everybody, you go home, you build your own individual models, and then we can come back and combine using the combination strategy that we are going to discuss later on. Now, so, and sometimes you have a kind of mixed mode, hybrid of the architecture, whereby you have sequential being combined with parallel. You know, this is in parallel to this guy. But in this parallel combination, this is going parallel to this one. However, in this one, you can see a kind of sequential. I will build these two in parallel. Then I have to combine, use a combiner here. This form is serial combination. Then finally, I'm going to combine these two together as the final combiner. So what this one is showing to us is sometimes we might have ensemble inside another ensemble. See, ensemble inside another ensemble. So that you can see here, this is an ensemble. This is one ensemble, which was developed by maybe participant A. So you will bring to us, okay, you decide to train like two models and then use them to combine them together to produce results. Then we need this, your result. There are other participants here. We bring from individual, and then finally we combine the output of your own. In fact, this is a team. This is called Adam team. This is our team A. From this group, we might have results from another team, just like this, coming together again. So our final result here might have to be combined with another team result coming. So in which case we are going to have a third level ensemble. I mean, you keep combining until you are able to achieve the best result that you envisaged. I gave you this example when we were discussing the real life advantages or demonstration of the importance of using ensemble techniques. When I told us about the very popular Netflix campaign, where teams from different backgrounds came together finally to combine their own works to produce the final and the best result. So in an ensemble, you have that liberty to keep combining the individual models until you get what you want. So you can see AI is one ensemble. This ensemble now is going to enter another combination system until we achieve the maximum possible outcome that we want. So today we are going to look into the categorization of ensemble techniques into heterogeneous or homogeneous. Now, when we say heterogeneous or homogeneous, what we are saying is this. Now, what is the constituent of this model? This model has been produced using neural network. In this case, we will say that this kind of ensemble is an homogeneous ensemble, because it is made up of the same type of algorithm. Neural network is neural network. Even if you try to manipulate it, single layer, two layer, or whatever, it is still from neural network. We call this homogeneous. This is what we want to look into now. How do you develop homogeneous ensemble? However, if we decide to say, okay, this is neural network, this one is based on supervector machine, while this one is based on maybe decision tree. Now, in this case, now we are having heterogeneous ensemble. It means you have developed the individual base model from different algorithms, heterogeneous ensemble. Now, so this is the categorization we look into briefly. So we say we have the homogeneous and then the heterogeneous. And based on the kind of, we can look into different training strategy and combination we are going to look into, which we just mentioned before. We have the parallel training, wherein you have with different training sets. We have the bagging and the voting. So we're going to look into how you are going to divide your data in such a way that it can generate homogeneous. So ensemble, that is, you have the same neural network is being used, but however, you are working with different training sets in a unique way. Then we have the sequential training, where you iteratively reweigh the training examples so that current classifier focus on hard examples, like boosting. So when we develop in such a way that, okay, we are going to be we'll be dividing the data repeatedly in different formats, or where we focus on, for example, when we build model 1, we notice that there are so many mistakes for a particular data point, D1. So the next training we're going to do, we will repeat that particular data in more time, repeatedly. We give it more weight so that the system can see many samples from the same data point. So hopefully they can get it right. So this is what we do in the sequential training category. However, when we look at homogeneous ensemble, just pay attention to this simple kind of mathematical setup. So in the homogeneous, we use the same arbitrary learning algorithm, but rather you manipulate different training data to make it learn multiple models. So that is why I put it this way, that in homogeneous ensemble, your data 1 is not equal to data 2, data 2 is not equal to data 3, data 3 is not equal to data m. See, even if they have, it's the same data set, it could be the same data set. However, you do resampling. So when you resample the data, the combination you're going to have is going to be different. And when the data set is totally different after the resampling, it is considered a different set. For example, we are using A, B, C, D, E. We divide it into training and testing. A, B, C is used for training. D, E is used for testing in this phase. This is phase 1. Phase 1. When we go to phase 2, we resample the data again. Now we have A, D, E for training and B, C for testing. Although the data is still made up of the same number of alphabets, however, the combination is totally different. This is ABC for training. This is ADE for training. We consider that this data set, this one is not equal to this. This is what we're talking about here. It doesn't mean you have to look for different data every time you want to build the base model. Otherwise, this is not possible. You see? Because the data set you have is always limited. But rather, you can use resampling to make the data to be different. Another thing you can do to make the data set to be different also is you might decide also to use different features, sub-features. Like we mentioned before, you use different sub-features. For this first data, for this first model development, I'm going to use like 10 feature, 1, 2, 3, 4, 5, 7, 8, 9, 10. The first 10 features. But the second model, I'm going to build it using 11 to 20 model number. That is the feature number 11, 12, 13, up to 20. These are taken from the same data set, but I'm using different subset of this data. So that is why we assume in that case that data 1 is not equal to data 2 up to the end. So, but however, the learner, that is the algorithm, which we call learner, are going to be the same thing. I'm using neural network. The same neural network, up to the end. So this is first one way of looking into homogeneous ensemble. It has its own advantages. However, based on experiences, it has been recommended that it's better to have different algorithms combined together. But that doesn't mean homogeneous. Sometimes homogeneous might be the one that works for you. And in most cases, it is easier to develop faster because you just need to specify that, the ensemble. You just need to specify the learner, the algorithm, and automatically different version of that algorithm will be built for you by the system. And then you just do the combination. But that doesn't mean it's the best. It is easier and faster to build. But then it could be better to also experiment with other ones that we're going to discuss. Now, so this is the basics when you are building the data. Now, there are different methods for changing the training data. One is called debugging. Here, you just resample the training data, just random resampling. You just resample the data every time. This example I just did here. Here it was ABC for training. Now it is ADE. If I do the third resampling now, third phase of resampling, maybe I'm going to have C, B, D as my training set, and then A and E will be for testing. That is bagging. Resample the training data. I don't pay special attention to any sample. But sometimes we might use boosting in the idea of weight. We reweight the training data. So in the first time, I might have A, A, B, C, and then D, E is used for testing. But the second one, I might decide to have, because we noticed that after the training, the first model, there was problem with B. Data point B was misclassified. So in the next model we are going to build, we will pay more attention to B, so we can have A, B, B. We allow B to repeat itself 2 times. Why? Another one is not even there. So A, B, B. So we repeat the data point that is being mistaken or that has been mistakenly classified in the previous model that we built, in the base model we built initially. So that the idea is that we want the second model to pay more attention to this misclassified entity. So by so doing, we give it more weight. We repeat it more. That means we need to finish this we need to finish building this one before we move to this one. That's how we call it. It's going to be sequential. It could be built in a sequential manner. However, for bagging, we don't care. We just do resampling, resampling, resampling. It means anybody can go and build the model. We just make, okay, use your sampling number to be this. 20 people, as many people as possible can combine together in parallel to build the system. So this one can be in parallel. While boosting, reweighting the training data will be sequential, because the outcome of the first model will determine the next resampling we are going to do. Which data point are we going to assign more weight will be determined by the outcome of the previous model, and then it continues like that. So we are going to see detail about how boosting is done. Now, in Weka, which is demonstrating a package for now, this kind of homogeneous ensemble, they are referred to as meta-learners. They call them meta-learners. What they do is very simple. They just take in an algorithm as an argument, the base learner. You just indicate in your Weka that, okay, I want to build an homogeneous ensemble using neural network. So the Weka will automatically create a new linear algorithm, as many as possible for you. It will create multiple ANN base while resampling the data every time. And then it will generate the final new algorithm, which is now the combination of all these algorithms that have been built. You just specify, okay, I want 21, or I want you to build 501 model from neural network while doing resampling. That is homogeneous ensemble. I hope we are following.
Yes.
Okay.
Yes, sir.
Thank you. The second is the heterogeneous ensemble, which if we remember in one of our previous introductory videos, we did mention that it is based on experiences. People recommend that it is better to go for heterogeneous, because when you are developing a system, you want people with different type of knowledge to come to it. So we want to build a very strong ensemble. It's sometimes good to have people that have different experiences. So we want to work on developing an ensemble or a very strong strategy for medical bioinformatics or whatever. So we have people from computer science, we have people from medical to collaborate together. We also have people with business-oriented ideas, so that you have people with different background coming up with the kind of looking at the problem from different angles. That would definitely make the outcome to be a little bit stronger, hopefully. An experimental result from history has always shown that heterogeneous ensemble will be stronger than an homogeneous, because ANN, for example, has its own hypothesis space. For example, AN always use this hypothesis space, H. So every neural network you train will take one from here. It started to be H1, H2, up to HN. These are the hypothesis space for neural network. So whatever base model you are going to take for the homogeneous is going to be taken from one space. However, when you bring in, this is for neural network. This is the hypothesis space for neural network. This is for SVM. This is a hypothesis space for SVM. It has its own H1, H2, up to HN. This is the one for decision tree. Decision tree. So H1 up to HN. So you can see the advantage of heterogeneous over homogeneous is you are having things from different hypothesis space. So I'm taking some from this guy, I'm taking from this, I'm taking from this. So the attributes, what this kind of model we see is different from the angle from where neural network is looking at it. Decision tree is also looking at from another background totally. So imagine combining this tree into an ensemble compared to when you combine it with all taken from neural network. So we can see a little bit of weakness in the homogeneous. But like I said, it has its own advantage in that it's very simple. You just specify that only algorithm and automatically the ensemble will be built for you. But for heterogeneous, now you have to take some further steps, specify different models, different learning algorithms that you are going to use. Now, so in heterogeneous ensemble, this is different. You use different arbitrary learning algorithms in a combined form. There are two ways of building this. One is either by keeping the data fixed to make the combination learn multiple models. You see, because the learner 1 is not equal to learner 2, and learner 2 is not equal to learner 3, up to learner M. All the models, all the algorithms we are using, they are from different type. So this is neural network. This is SVM. This is support vector, sorry, this is decision tree. In between, we have naive Bayes. So you are combining different models. In this case, your data set can be the same. It's not a problem. So we're training each algorithm using the same data. That's why here we say data 1 is equal to data 2 is equal to data up to the last data. So the original data given to me for training, I just supply it to each of them. Because they are different algorithms, so I'm giving them the same data, that's okay. You cannot do that for homogeneous ensemble because they are all neural network. So if you give them the same data, you're going to be building the same, you're going to having the same model at the end of the day. And the essence of ensemble is that your base classifiers, which you want to combine later, must have diversified outcome. The outcome coming from each model you are training must be different. That is why they can take advantage of their combination to achieve better results. And this is what we demonstrated here. Let me remind you. You can see this one here. This is why if all these models are produced, they are making the same mistake. Let's say all the mistakes are from this. You can see that we might not be able to achieve 100%. But while this one is making this mistake, this one is getting it correctly. The mistake that this one is making, the other one is not making the same mistake. That is what we call having diversified base learners. So when your individual base learners are having different characteristics, different outcome, then it can really assist you in getting the combination that will be better and accurate, that will be more accurate than any of the individual participating base learners. So this is the essence. And that is why it does not make any meaning to have data 1 equal to data 2 for homogeneous, because you are using the same hypothesis space. But in this case now, heterogeneous, we are using different hypothesis space. Neural network, SVM, naive Bayes, decision tree, so we can fix the data. In that case, you don't need to do any resampling. This is one. The second possibility for heterogeneous ensemble is to manipulate different training data to make the combination learn multiple models. See, you manipulate different training data to make the combination learn multiple models. That is, in addition to the fact that the algorithms are totally different. This is SVM, support vector machine. This is naive Bayes, and this is decision tree. You also decide to manipulate the data at the same time. That's up to you. See, this is another way you can do. This is valid. This is also valid. So that why, even though they are different algorithms, so keeping the data fixed, it's okay. That's going to produce diversified outcome already. However, some people say, I want it even more diversified. You see, I want it even more diversified. It's okay, that's up to you. In that case, you decide to do different resampling of the data. That's one way of doing it. You resample your data, as we have described earlier. You might even try to play with the features. You use feature 1 to 5 for one, feature 6 to 10 for another one, feature 11 to 14 to another one, feature 15 to 6. You just make sure that the data set is not the same thing. Data 1 is not equal to data set 2 up to all the data you are using. So it's like you are doing here, you're only making sure that two things are not equal. You're only making sure that only one thing is not equal, and that's the algorithm. You make sure that algorithms are different, and that is heterogeneous based on the algorithm differences. But in this case, you are manipulating two variables now. You are making sure that the algorithms are different, and at the same time, you're also making sure that even though the algorithms are different, the data set that is entering each algorithm is also different from one another. So that is, you are manipulating. So this one is going to take more time. This one will take more time compared to this one. But then, hopefully, we arrive at better result. But then, somebody will be wondering, then which one is better? So we always remember this is our principle. Let the data speak. Let the data speak. And I always recommend to people that don't always start from the most complicated level. Start from something simple. This is one of the principles of machine learning. Start from something simple. Use individual model first. Build only one model. See how you can improve the accuracy. It is when there's no one single model you can get that is getting what you need, then you start moving towards Ensemble. And when you go to Ensemble now, why don't you start with simple Ensemble, homogeneous? Just pick neural network, let the system build for you several neural networks, and then combine them. If an homogeneous Ensemble can do the work for you, why do we need to spend more time building heterogeneous Ensemble? So this is the principle of machine learning. You start from something simple. If an individual model will work for you, you don't go for Ensemble. But it is when the individual model, you have tried a couple of individual models that you know from experience are very, very good, very strong models, but then they have not been able to achieve your aim, then you move to Ensemble. Even in Ensemble now, we made it to realize there are different levels. The homogeneous is very faster and very easy to develop. You start with homogeneous first. If homogeneous Ensemble can get you the needed excellent result, you don't need to go to heterogeneous because heterogeneous will take more time. However, if homogeneous failed, then we move to heterogeneous Ensemble. This is the pattern of moving. And even if it failed, we might have to consider a mixture of homogeneous and heterogeneous in an hybrid setting. We are going to go there later, we discuss it. It means we build first level of Ensemble, we build like 5 ensembles, and then we combine the result of this ensemble together again. That is like a loop. We have an ensemble inside another ensemble, and we can have many layers of ensemble. Ensemble stage 1, we build 5 ensemble, we combine them. Another team build another 5 ensemble, combine it again. Another team 3 build another 5 ensemble, combine it again. And all of us, team 1, team 3, team 4, we come together and combine our ensemble result again. We can have that level of cascaded ensemble. It has no limit. We keep going until we get what we want. So, however, remember, let the data speak. It's always good to let your data determine what you need to do by starting from something simple. Because I've seen people, they started with something very complicated and they achieved lesser result compared to, of course, they finally got something good, something excellent, but then we check it out and found out that we could even get the same result from a simple algorithm. It means they did not explore the simple form before they start going complicated. So this is not the way of machine learning. Rather, we let the data speak. Somebody will ask which of this method is better. It depends on your data. You can see, you might have data set that a very simple algorithm will get you the best results. You don't even need to go to Ensemble. And you might have very complicated data that Homogeneous might not work. You might have to keep going until you are able to get more diversified ensemble-based learners that can work for you. So these are the two types of categories, types under the categorization based on homogeneous or heterogeneous. Now, I hope that is clear. So if there's any question, we can take one or two questions. Otherwise, we move to the next point we're going to make as we proceed. Now, so we say steps in ensemble method development. So there are majorly three steps when you want to develop ensembles. The step one is for you to develop multiple machine learning models. See, you develop multiple machine learning models. You need to generate them. It could be using the same algorithm or different algorithm. We just discussed. If you are using the same machine learning algorithm, then you are developing homogeneous ensemble. If you are using different machine learning algorithm, then you are generating heterogeneous ensemble. So once you do this, this is what we call base learners. How do we generate it? We have discussed that. Now, once you generate the base learners, it could be, I want to generate 3, then I want to generate 5, I want to generate 7, be as many as possible. We've heard of real-life example whereby they got the best results when they generated 105 system. When they generated 105 system, that was when they got the best result possible. 105 base learners. It's a possibility. Now, yeah, that's a possibility. So once you are done with the first step, which we have described how to do that, so you train, that is, you first generate multiple machine learning models by either using the same algorithm or using different algorithms, which we produce homogeneous or heterogeneous ensemble respectively. The next step is to do the prediction, carry out prediction based on the base model. You see, now you have trained, then you need to predict using what you have trained, because training is just the beginning. Now you have to do prediction using those models that you have trained. So what is now the outcome of your prediction? It is those outcomes of the prediction that we are going to use in step 3 to combine prediction outcomes into one single output. Combine prediction outcomes into one single output, which is going to be your final results. So these are the 3 steps that usually you should make use of when you are developing ensemble model. Now we move to the concept of the techniques of ensemble method. How do we generate final output? That is, how do we combine the results? See, I haven't developed multiple machine learning models by training machine learning algorithms, then let them predict, then finally we combine the result. No, so how do we do this combination to generate the final outputs? So there are options. There's the simple voting, very simple voting method. Then we have the bagging, which depend mostly on bootstrap aggregation. So it is generally believed that voting might improve prediction, but then depend on the kind of voting, as we are going to see. Then we have the bagging, the bootstrap aggregation, which could decrease the variance of your model. We have the boosting, which could reduce the bias. And of course, we have the stacking, which by far not very much in use yet, but then I see a lot of potential in this option as it tries to solve the problem of bagging and boosting and even the problem of voting methods. So, because sometimes when you say, okay, I choose yes or no, majority carries the vote might not always be correct, as we all know. So, of course, that's democracy. Sometimes you might say yes, 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 ignoring the performance or the performance measure or the experience of the people that are involved. So if an algorithm is saying yes and it has higher accuracy, I think we should give it more votes when it comes to that reality. But then if you are using simple voting, we don't care where the person comes from. Everybody gets the same number of votes, which could be a problem. Now let's look at this simple method of voting that I often use. Here, sometimes we may have the one we refer to as the simple method for voting. It might be the one with the maximum voting. So, okay, these are algorithms that you have trained. This is model 1, model 2, or colleague 1, colleague 2. These are model already trained. So this one selected 5, this one selected 4, 5, 4, 4. So we have maximum voting. 4 people selected 4. So the final rating we are going to give is going to be 4. So maybe we have 1, 2, 3, 4, 5 options to choose. 3 people selected 4. So we choose the majority. So we call the maximum voting. Sometimes it might be averaging. So maybe the problem you are solving is actually regression problem. Regression problem in the sense that you want to predict numbers. You want to predict the age. So in that case, you might have to find the average of the output that has been given out by each of the trained models. So the average is going to give you the final result. This is often used when you are dealing with regression problem. And then we have what we call the weighted average. The weighted average is a case whereby we don't just want to use average directly. We don't want to use average directly, but rather sorry. So in the weighted average, we don't just take the average, but rather we assign some weight to each of the model, maybe by chance or based on expert opinion. That it is natural. So we have someone that this is a medical doctor with a lot of experience. Your colleague number 1, you know, this is a professor of medicine. He has so many years of experience. We say, okay, whatever decision he takes is going to be 0.23. The second guy is also given 0.23, but newly trained doctors are given 0.18. So that whatever decision they are taking, the weight assigned to them, we bring the effect of that weight down. Sometimes we use this kind of idea. So in which case, if it is still dealing with regression, then we are going to have to calculate it as those. Now, so the output is going to be calculated by multiplying their results, their rating, multiplied by the weight, and then sum it together to find the average. This is weighted averaging. Sometimes also in the maximum voting, we can also implement it, in which case you have to assign them not real number, but constant value. So in which case, colleague 1 is assigned a particular value that, okay, whatever he says, whatever he picks is like 2. If you say 5, it's like 2 people are saying times 2. So this one is saying this one is 1, this one is 2, it's 1, it's 1, it's 1. So whatever vote this man is selecting is going to be counted 2 times. We also do that for in the voting. That's going to be weighted voting, in which case we give more kind of more weight to the people we think they are more experienced. In terms of our model, we give more weight to those models that are having higher accuracy. Let's say this is our model 1. It achieved 98% accuracy in training, in testing. This one achieved 92%. This one achieved 83%. So this one with 98%, we hope that we can give it more weight because it's higher value in terms of testing. However, one of the problems with that is later, as we are going to see it, when we discuss boosting and its challenges, anytime it makes mistake, because the fact that you have 98% accuracy you're having an error of 2%. Once we decide to multiply the outcome of this guy with 2, then it means whenever it makes mistake, we are going to multiply its mistake by 2 also. These are challenges with this idea. And that is why finally, when we move on, we are going to all see why and how stacking is a better option to all this, some of this idea based on my personal experience and the experience of some other practitioners. That stacking, we try to avoid some of these challenges. Now, it seems somebody was raising hands. Perhaps it's time to, yeah, it's time to, okay.
No,
yeah, we are going to take some questions now. Yeah.
I don't know, maybe because I lost connection. I think weighted average is the same thing as boosting. Am I right? Hello?
Hello?
Hello? Weighted averaging. I said, is it the same thing as boosting?
Okay, thank you for the question. Yeah. See, there are simple methods and there are methods that are a little bit considered to be on the complex side, which we are going to take later. Yeah. Yeah, bargain is when you ignore, we don't care about your own performance measure, your experience, everybody, you have the same voting right. Yeah, this is one simple way to look at bargain, okay? That is a simplistic look at bargain, yeah. However, when we develop bargain as a comprehensive method, there are other ways of looking at bargain, looking, okay, how do you resample your data? You see, resampling the data itself might mean that, okay, we just resample our data randomly. So that will also qualify it to be called bargain. So bargain will be considered in 2 levels. I mentioned this before. At the level of data creation, when you are creating your data for the training of those base learners. So we just have random partitioning, which is resampling. See? So we use bargain in this sense. But at the same time, when you are considering the output, see, how do we combine the output from different classifiers? Then this is the bargain, the one you are mentioning now. Okay, if it is bargain, we just consider your output. We don't give weight to anybody. You are on the same level. However, for boosting, we'll look at it from the side of your data partitioning. When you want to build homogeneous ensemble, you want to play with the data. So in the first stage of the data, every data has the same weight. In the second stage, we give more weight to a particular data point to repeat it. We want it to be repeated. Why another data point is not even going to be selected? Like the example I gave a few minutes ago, that, okay, this particular data point, because there was a mistake before, we want you to let it get repeated in the next stage of your base learner development. But however, when we are not talking of the combination of the outputs, so that's why when you're talking of bargain boosting, we have 2 ways to look at it. We look at it from the point of view of data set preparation for the development of the base learner. And we also look at it from the point of how do we combine the results. So when we are combining results, yeah, your question is right in the sense that we're talking of boosting as the one that is given more weight to the one that is trusted. Okay, your output is very correct. I think we should trust whatever is coming from you. So if you say yes in your voting, we're going to multiply your yes by 2. Meanwhile, that also means that if there's a mistake from you, your mistake is going to be multiplied by 2. That is when you look at boosting from that particular point of view. But then the good thing is we are going to take each of them one after the other. We're going to take voting, we're going to take the bargain, and then we're going to take the boosting individually, and we go into details of how you can deal with them, starting from the data manipulation till the final output that's going to be produced. I hope I answer your question, Doctor.
Yes, sir.
Okay, thank you.